Welcome to lecture 32. This is week 7 and we are talking about gradient based methods for unconstrained multivariable optimization. In the previous week, we have talked about Cauchy's steepest descent method. In this week, we will talk about another gradient based methods named as Fletcher-Reeves conjugate gradient method. But before that, we will make some comments about Cauchy's steepest descent method. Cauchy's steepest descent method zigzags its way towards the optimum point. If you look at the figure, it will be clear that when you start from x 0 and go to x 1, then go to x 2 and then go to x 3, you take a zigzag path. This is because each step is orthogonal to previous step. In other words, each step is perpendicular to the previous step. So, the entire sequence of paths will look like a zigzag way. This can be very easily shown that steepest descent method zigzags its way towards the optimum point. Remember the update rule of steepest descent method, which is x k plus 1 equal to x k plus alpha k s k, where alpha is the step length and s k is the search direction, that is gradient of the function at current estimate x k. Alpha k is obtained by minimizing the function f x k plus 1, which is f x k plus alpha k s k, and you know that to determine this alpha, we will set dfd alpha equal to 0 and solve the resulting equation. Now, upon differentiation, we get gradient of f at x k plus 1 into s k is equal to 0. Note that x k plus 1 plus alpha k s k is same as x k plus 1. So, upon differentiation we get that gradient of f at x k plus 1 into s k equal to 0. That means, the search direction, which is a vector. So, the product of search direction vector at kth step and the gradient vector at k plus 1 step is equal to 0. That means, they are perpendicular to each other. Now, the search direction at k plus 1th iteration is nothing but the minus of the gradient vector at k plus 1. This is what we know from steepest descent method. So, we can write the search direction vector at k plus 1 into search direction at kth step is equal to 0. That means, two consecutive search directions are orthogonal to each other. So, that is why you see that the steepest descent method zigzags its way towards the optimum point. Remember, this result is true only if the line search is performed exactly. That means, the value of the alpha k is determined exactly. So, what is the role of step length in gradient based methods? The update rule of a gradient based method requires a step length controlling the amount of gradient updated to the current point at each iteration. Because we have seen that x k plus 1 is x k plus alpha k and s k. So, this is the gradient and this is the step length. So, the step length decides how much we will move in the direction of such direction vector. A too large step length can lead to divergence. A too small step length will take much longer time to converge. That is why we need an optimum step length, so that we get convergence and we get convergence in minimum time. There are two methods to find the step length which are commonly used: the backtracking line search and the exact line search. The backtracking line search is an inexact line search, and the exact line search finds the alpha k exactly, whereas backtracking or inexact line search finds an approximate value of the step length. So, this is what happens when I use a step length that is too large. You see, the search direction starts oscillating. When you take too small step size, it takes too long time to hit the minimum. The minimum is shown by the star, and we are showing a two-dimensional function's contours. Similarly, when you find an appropriate step size or step length, you will get convergence, and you will get convergence in not so many iterations. We want to make another comment on steepest descent method. This is about scaling. Let us consider two quadratic functions as shown in the figure. The first one is x1 square plus x2 square, and you can see the contours are all perfectly circular. Now, if I consider the second function, which is x1 square plus a x2 square, then depending on the value of the parameter a, the contours may be circular or may be elongated. If a equal to 1, this equation reduces to the first equation and the contours become circular. But if I take large value of a, the contours will be elongated as shown. Now, you can note down that the first function x1 square plus x2 square, if I start, let us say from this point, you see that the search direction directly points to the minimum. It is a two-dimensional function and x1 square plus x2 square. So, the minimum is 0. But for the second function x1 square plus a x2 square, you see that it takes longer time for the steepest descent method to go and hit the minimum at x1 equal to 0, x2 equal to 0. the function value equal to 0. So, what we learn is that for a quadratic function whose contours are circular, the search direction in case of steepest method will directly point towards the minimum. But if the contours are elongated, then the convergence will be slow, because in that case the search direction does not directly point to the minimum starting from any arbitrary point. So, speed of convergence is related to the condition number of the Hessian matrix. The condition number of a symmetric positive definite matrix is the ratio of largest to smallest eigenvalues. The condition number of a symmetric positive definite matrix is the ratio of largest to smallest eigenvalues. Condition number may in general be defined as the ratio of the singular values, but in case of symmetric positive definite matrix, the eigenvalues and the singular values are same. So, the condition number of a symmetric positive definite matrix is the ratio of largest to smallest eigenvalues. For a well conditioned Hessian matrix, the condition number is close to unity. If the condition number is close to unity, the contours will become more circular and the steepest descent method will work very well, because in that case the search direction will directly point towards the minimum. Consider the function x1 square plus a x2 square, compute the Hessian and you get the matrix 2 0 0 2a. So, the eigenvalues are 2 and 2a. So, the condition number is 2a by 2 equal to a. So, when the condition number is 1, that means a equal to 1, the convergence is fastest. So, now again consider the function x1 square plus a x2 square. So, now if I perform appropriate scaling and if it is possible for me to redefine the function x1 square plus a x2 square as y1 square plus y2 square in terms of new variable y1 and y2, then the contours of this new function y1 square plus y2 square will be circular and steepest descent method will work very well. So, it is possible to do it here. Note that if I redefine y1 equal to x1 and y2 equal to root a into x2, then the function f equal to x1 square plus x2 square can be written as g equal to y1 square plus y2 square. Note that for this function, the condition number of the Hessian matrix will be 1, because for this function the Hessian will be 2 0 0 2. So, condition number is a positive symmetric definite matrix, symmetric positive definite matrix. So, the condition number will be 2 by 2 equal to 1 and the contours will become perfectly circular and the steepest descent method will work very well. In general, how do I perform scaling? So, to perform scaling, we define the new variable y and take a diagonal matrix T and scale the variable as x equal to T y. So, in terms of new variable y, I can scale the variables as x equal to T y, where T I have to choose as a diagonal matrix. So, the new function will be now say g of y equal to function of t and y. So, the gradient of this new function, gradient g, can be computed as transpose of t into gradient of old function f. Similarly, the Hessian of the new function can be computed as Hessian of g equal to transpose of t into Hessian of old function f into matrix T. So, we have to choose the matrix T as a diagonal matrix such that the Hessian of the new function g has condition number close to unity. Let us now make some more comments about steepest descent method. Cauchy's steepest descent method works very well when we start far from optimal point. It has linear convergence. If an exact search direction is made at each iteration, two consecutive search directions will be orthogonal to each other, and the steepest descent method will zigzag its way towards the optimum. In most implementations, the search directions are scaled such that the length of the search vector is 1. So, for minimizing a function, we can scale the search direction by dividing the gradient by the norm of the gradient. So, instead of taking the search direction s at kth iteration as minus gradient of f at x k, we take s k equal to minus gradient of f at x k divided by norm of the gradient of f at x k. If the objective function is not convex, we can find local minima while minimizing. But if the objective function is convex, you know that local minima is also a global minimum. We may also get stuck at a saddle point, but these are the characteristic feature of any gradient based method. Now, we will talk about conjugate gradient method. The steepest descent method works well when you start far from the optimal point, but the convergence becomes very slow as the optimal point is approached. The convergence characteristics of the steepest descent method can be improved greatly by modifying it into a conjugate gradient method. This was first proposed by Fletcher and Ives in 1964. The conjugate gradient method can be considered as a conjugate directions method that uses the gradient of the objective function. Any minimization method that uses the conjugate directions is quadratically convergent. Such methods will minimize a quadratic function of n variables in n steps or less. Powell's conjugate direction method requires n single variable search per iteration. We then find new conjugate direction at the end of each iteration. Therefore, to find the minimum of a quadratic function, in general, Powell's method requires n square single variable search. But if we use gradients of the objective function, we can set up a new conjugate direction after every single variable search, and hence we can achieve faster convergence. The conjugate gradient method combines current information about the gradient vector with that of gradient vectors from previous iterations to obtain the new search direction. The proposed search direction for this method is a linear combination of the current gradient and the previous search direction. So, the search direction becomes a linear combination of the current gradient and the previous search direction. So, the search direction S at k plus 1th iteration is minus gradient f at k plus 1 plus norm square of gradient at k plus 1 divided by norm square of gradient f at kth iteration into search direction at kth iteration. So, basically the search direction at the current step is a combination of the current gradient and the previous search direction. So, this can also be written as minus gradient f plus gradient f transpose into gradient f divided by gradient f transpose into gradient f. The numerator one is evaluated at k plus 1th iteration, that is x k plus 1, and the denominator is evaluated at x k, and the search direction is evaluated at x k. That means, search direction from the previous step. So, in case of conjugate gradient method, the current search direction is always a linear combination of the current gradient and the previous search direction. So, the difference with the steepest descent method is this, that in case of steepest descent method, the search direction is the current gradient direction, negative of the current gradient direction, but we add this information from the previous step in case of conjugate gradient method. Note that the conjugate gradient method is a first order method. We are still using first order informations, only first partial derivatives are involved. This method represents a major improvement over steepest descent method with only a marginal increase in the computational effort. Note that only this information about the previous search direction is included in the current gradient information. So, there is a marginal increase in the computational effort, but there is a major improvement over steepest descent method. So, where is the algorithm for conjugate gradient method? In the step 1, we start with an arbitrary initial point x 0. Step 2, we set the first search direction as s 0 equal to minus gradient of f at x 0, which is same as steepest descent method. In the step 3, we find the point x 1 according to the usual relation x 1 equal to x 0 plus lambda 0 into s 0. So, where lambda 0 is the optimal step length in the direction s 0. That means, we need to perform the line search. We set k equal to 2 and go to the next step. In the step 4, we find the gradient of f. Let us consider this is as kth step. So, we find the gradient of f at x k and set the search direction for k plus one step as s k plus 1 equal to minus gradient at x k plus 1 plus norm square of gradient evaluated at x k plus 1 divided by norm square of gradient f evaluated at x k into such direction at x k. So, such direction at x k plus 1 is the linear combination of the gradient at x k plus 1 and the such direction at x k. Now, compute the optimal step length lambda k in the direction s k by doing line search and find the new point as x k plus 1 equal to x k plus lambda k s k. If the convergence is achieved, we will stop. To understand the convergence is achieved or not, we have to check the magnitude of the gradient. So, if the norm of the gradient is very small, we will assume that the convergence is achieved, we will stop. Otherwise, we will set the value of k equal to k plus 1 and go to again step 4, where we find the gradient and then the search direction and proceed. So, this figure schematically shows the functioning of steepest descent method and conjugate gradient method. Note that the steepest method takes zigzag path to the optimal point and takes many more iterations compared to conjugate gradient method. Now, let us take an example. We are considering a quadratic function, 2 variables, and we will solve. That means, we will minimize this function using conjugate gradient method starting from the point x 0, which is 0 0. So, in the iteration 1, the gradient of the objective function is evaluated first. So, you take del f del x 1 and del f del x 2, they are evaluated as 1 plus 4 x 1 plus 2 x 2, which is del f del x 1, and minus 1 plus 2 x 1 plus 2 x 2, which is del f del x 2. So, put the value of x 1 equal to 0 and x 2 equal to 0, and we get the value of the gradient at x 0 as 1 minus 1. So, initially the search direction is minus of gradient at x 0. So, the search direction is minus 1 1. Note that the gradient is 1 minus 1. So, the search direction is minus of the gradient. So, minus 1 1. To find x 1, we now need to find the optimal step length lambda 0. For this, we minimize f of x 0 plus lambda 0 into s 0 with respect to lambda 0. So, let us now evaluate f of x 0 plus lambda 0 s 0. You know x 0 equal to 0 0 and s 0 is minus 1 1. So, this becomes f of minus lambda 0 lambda 0. So, we evaluate f of minus lambda 0 by putting x 1 equal to minus lambda 0 and x 2 equal to lambda 0 in the original expression for f, and we get that as lambda 0 square minus 2 lambda 0. So, f of minus lambda 0 equal to lambda 0 square minus 2 lambda 0. So, to find out the optimal lambda 0, we will set d lambda 0 of f, which is lambda 0 square minus 2 lambda 0 is equal to 0. So, we get as 2 lambda 0 minus 2 equal to 0, and then we get lambda 0 optimal is 2 by 2 equal to 1. So, we get lambda 0 star as 1. So, once we get that, we can find x 1 as x 0 plus lambda 0 into s 0. So, x 0 is 0 0, lambda 0 I have obtained as 1, s 0 is minus 1 1. So, x 1 is obtained as minus 1 1. So, find out the gradient of f at x 1, and we can find the gradient as minus 1 minus 1. So, now we proceed to the next iterations. So, we obtained gradient of f at x 1 as minus 1 minus 1. So, in the iteration 2, we first now find the search direction S 1, which can be obtained as a linear combination of the gradient at x 1 and the search direction at x 0. So, let us first find out the norm square of f, the norm square of gradient of f at x 0 and norm square of gradient f at x 1, which are obtained as 2 and 2. So, you can now find the search direction at x 1, which is obtained as 0 2. So, again minimize f of x 1 plus lambda 1 s 1, because we have to find out the optimal lambda 1 now, and this is obtained as 4 lambda 1 square minus 2 lambda 1 minus 1. So, we have to now take d d lambda 1 of 4 lambda 1 square minus 2 lambda 1 minus 1 equal to 0, and if we do that, we will get lambda 1 star is equal to 0.25 or 1 by 4. So, x 2 is obtained as x 1 plus lambda 1 into s 1, and it is obtained as minus 1 1.5. In fact, x 2 equal to minus 1 1.5 is the optimal solution. To check that this is optimal solution, let us find out the gradient at this value x 2, and we find that the gradient is 0 0. So, gradient 0 is the first order optimality criteria, if you remember. Also, find out the norm of the gradient of f at x 2, which is 0. So, S 2 will be 0. So, there is no such direction to reduce the function value further. So, it shows that x 2 minus 1 1.5, that means x 1 equal to minus 1 and x 2 equal to 1.5 is the optimal solution. So, this is how the conjugate gradient method works, and you see that we had a 2 variable quadratic function, and we could get the optimal point in exactly 2 iterations. With this, we stop our discussion on conjugate gradient method here.